Okay, so let's compare and contrast AM and DSB modulation in terms of simplicity and power efficiency. In this section, I will talk about how simplicity and power efficiency has a crucial impact on the modulation design. Um, what is modulation and what is its significance in communication systems? Modulation refers to the process of modifying a high frequency carrier signal to encode information and enable it to carry data over long distances. In a communication system, modulation is essential because it allows the signal to travel long distances without significant degradation or attenuation. By modulating the carrier signal, the information is converted to a higher frequency that can easily travel through the atmosphere or any other medium. Without modulation, long distance communication would be difficult or impossible, and the signal would be too weak or susceptible to interference to be effectively transmitted. Okay, so simplicity and power efficiency are two key factors in modulation design. Simplicity refers to the ease of implementation and demodulation of a modulation scheme, while power efficiency refers to the ability to transmit information using the least amount of power possible, thus being more efficient. There should be a balance between simplicity and power efficiency in designing a modulation system to ensure optimal performance. Okay, so um, let's let's talk about real-world examples of modulation designs. Modulation designs that prioritize simplicity are often used in applications where the signal fidelity is not crucial and where the focus is on transmitting information with minimal distortion. On the other hand, modulation designs that prioritize power efficiency are often used in applications where power consumption is a critical factor, such as in battery operated devices or in systems with limited power supply. In the diagram below, I have provided a modulation design of a simple amplifier which is commonly used. Okay, so let's compare AM and DSB modulation in terms of simplicity. Modulating signal is typically an audio signal that is being transmitted over a radio frequency carrier wave for which it does not need a separate carrier signal. Hence, only a single sideband transmission occurs. The result is a modulated signal that can be transmitted over a long distance. Whereas in DSB, the carrier wave is suppressed, resulting in a signal that contains the upper and lower sidebands. In DSB modulation, both the upper and lower sidebands are transmitted, resulting in a signal that contains twice the information as an AM signal, as it has been generated from two identical sidebands combined with a separate carrier signal. This table shows that AM is simpler than DSB. Um, okay, so what are the basic principles of power efficiency in modulation? The power efficiency in modulation is a measure of how well a modulation scheme utilizes the available power to transmit information. A more power efficient modulation scheme uses less power to achieve the same or better transmission quality compared to a less power efficient scheme. Here I've provided the equations of calculating power efficiency from the modulation index. Always remember that the useful power would always be the upper and lower sideband power. Like here, as you can see, both for upper and lower sideband power, it's mu squared by 4. So always remember that the upper and the lower sideband power are the useful power, and the extra inefficient power comes from the carrier signal. Okay, so let's talk about the factors that affect power efficiency in AM and DSP modulation. So factors that affect the power efficiency in AM and DSP modulation include modulation index, which affects the amount of power used to transmit the modulated signal, as well as any distortion in the signal due to imperfections in the modulation process. In AM and DSB modulation, higher modulation frequencies and more complex waveforms require wider bandwidth and higher transmission power, which results in lower power efficiency. Simple waveforms such as sinusoidal or square wave modulation require less transmission power and offer higher power efficiency. Therefore, the choice of modulation waveform and bandwidth is carefully considered to achieve the best balance between power efficiency and performance. Okay, so um, modulation index represents the extent of signal amplitude variation in AM and DSB modulation. It determines the amount of power that is transmitted in the sidebands and the carrier, and it is essential to maintain a balance between the power efficiency and signal quality. A higher modulation index results in increased sideband power and a wider bandwidth, which can lead to spectral inefficiency and intramodulation distortion. Therefore, proper modulation index selection is crucial for achieving optimal power efficiency and signal fidelity. Here down below, I've provided equations for calculating the modulation index of AM and DSP. Um, Here in this slide, you can see that when the modulation index is less than 1, under modulation occurs. When the modulation index is equal to 1, the critical modulation occurs. And when the modulation index is greater than 1, over modulation occurs. Uh, Here, the graph compares the power efficiency of AM and DSP modulation as the modulation index changes. For AM, we can see that the power efficiency does not increase by much as as the modulation index increases, whereas for DSP, the power efficiency increases by a great extent as the modulation index increases. Okay, now let's talk about how simplicity and power efficiency have impacted the real world modulation designs. We're going to talk about AM and FM, which are very popular broadcasting systems. In terms of simplicity, AM broadcasting is simpler than FM broadcasting because it requires less complex circuitry and is easier to modulate and demodulate. However, in terms of power efficiency, FM broadcasting is more efficient because it can transmit a wider frequency band and has a higher signal to noise ratio, which results in less interference and better sound quality. Overall, FM broadcasting is more complex but more power efficient compared to AM broadcasting. Here I've created a table which compares AM and FM broadcasting systems in terms of simplicity and power efficiency. I have included this illustration because it gives a good visual representation of AM and FM modulation. Let's talk about the future of modulation. Future trends in modulation design include the potential use of machine learning and artificial intelligence to improve modulation techniques. This can lead to more efficient use of the available frequency spectrum, higher data rates, and better signal quality. In addition, the use of advanced modulation techniques such as orthogonal frequency division multiplexing and multi-carrier modulation can also improve the efficiency and reliability of communication systems. Overall, the future of modulation design is focused on maximizing efficiency and performance while minimizing the impact on the environment. This table sums up the simplicity and power efficiency of AM and DSP modulation. Thus, we can conclude that AM is simpler but less power efficient, whereas DSP is more complex and more power efficient. These are some visual representation of the simplicity and complexity of AM and DSP transmission circuits.